Hi, we are looking at the second subtopic of the electric potential. Okay, so number 2 is our electric potential. The symbol is big capital letter V. Okay, so first we're going to look at the concept of electric potential. Okay, that is our concept. Okay, electric potential. What is electric potential actually? At a point. Okay, so we define the electric potential. So I use EP as a short form. So electric potential at a point in a circuit is the amount of electrical potential energy in 1 coulomb of charge at that point. Okay, but to define this, we must have what sort of reference point. Okay, so the reference point is normally considered as zero potential, which is the earth, the ground is a zero potential. Okay, so this one is relative to a reference point. Okay, reference point, which is normally the zero potential. Okay, point, right? Zero potential point. So that is the reason, because there is no absolute value of electric potential. You must refer to something else. Okay, refer to some other point which makes sense. For example, a lot of our potential when we measure, we relate it to the earth. Okay, the earth is a gigantic place where you can assume entirely the potential is zero. Okay, it's zero. So that is the concept of electric potential. So it is at a point in a circuit is the amount of electrical potential energy in 1 coulomb of charge. It is per coulomb. So that means from here we can actually get a formula for the electric potential. So the electric potential V is actually equal to the energy, okay, the amount of electrical potential energy divided by the charge, okay, by the charge. But normally that electrical potential energy, when it passes through a certain device or a conductor, it is used to do work, and that work is normally equivalent to the amount of electrical potential energy possessed by the charge. So it's finally changed to this. Okay, so this is our formula to actually calculate the electric potential at a point. If you know the work done by the charge, okay, and that's the main problem. We cannot actually measure directly what is the work done by the charge, okay, because of losses here and there in the circuit. All right. So that is our first one, the concept electric potential. Now, the second one is the potential change. Okay, the potential change, normally the symbol we use is delta. Okay, is delta V. So when we say something about changes in physics, okay, in terms of physics, we normally refer to 2 points. It must have 2 points. The point where you start and the point where you finish. So the changes will be the condition at the final or your finishing point minus the condition of the initial point or the starting point. So let's say you have a circuit with a resistor. It can be 2 resistors. You start with point A, and here is point B and point C. Let's say current start from A. It flows from A to C. Okay. Now remember this. Current flows from high potential to low potential. So when we assume current flowing from A to B to C, it means the potential at A is higher than B, and then subsequently potential at B is higher than C. So it makes sense to say that potential at A is also much higher compared to point C. Alright? So let's assume again this is our resistor R1 and this is resistor R2. So when you say what is the potential change between A and B or from A to B, okay? So let's say from A to B, the potential change at B is equal to the potential at B minus potential at A, okay? Now, we already know that potential B is lower than A, so that means you're using a smaller number minus a larger number, you get a negative. So that means this changes is negative, alright? And then if in the reverse, from B to C, from B to A, then the delta VBA will be VA minus VB, which is the reverse of the delta VAB, and this one you're going to get a positive value. So that means potential change can have positive and negative, depends on how we analyze the circuit. Alright. Now, when we take the magnitude of both, okay, magnitude of both, that means delta VAB and delta VBA, they are actually the same. So that magnitude, okay, the magnitude of either VAB or the magnitude of VBA is called the potential difference. Okay, potential difference. All right. So that is normally the symbol same as a V. Okay, except potential difference normally refer to the magnitude of the potential change. So just remember, potential change means the final potential minus the initial potential. Alright, so that is the second one, the potential change. Okay, next one is that potential difference is actually different from the previous one we talked about when we talked about internal resistance, which is the EMF. Okay, so now we'll look at the difference between potential difference and EMF. Okay, the difference between EMF and potential difference. Okay, the difference between potential EMF and potential difference. So potential difference, first we'll look at this one. Potential difference we can use short form. Okay, potential difference between any 2 points is the amount of energy dissipated, or in other words, loss. Okay, loss. Right. So potential difference of PD in between any 2 points is the amount of energy dissipated or lost per unit charge. Okay, per unit charge. So that is loss. When you talk about potential difference between any 2 points, you are talking about the loss or the dissipation of energy, amount of energy dissipated between that 2 points for every 1 coulomb of charge passing through. Now, the difference between the EMF and this one is this. EMF, which stands for electromotive force. Okay? It is actually not a force. It's very confusing when you put a force there, but it's actually a voltage. So EMF stands for the electromotive force. This one is between any 2 points. Okay, any 2 points. But this is a bit special when you talk about any 2 points here. These 2 points normally refer to the positive and the negative terminal of the battery. Okay, because EMF normally refer to the ability of the battery. So EMF between any 2 points is the amount of energy supplied by the battery per unit charge. You see the difference? Potential difference talk about amount of energy dissipated per unit charge, but this one is amount of energy supplied by the battery, okay, per unit charge. So that is the main difference between the potential difference and also the EMF, okay. Or you can say that EMF is the largest potential difference in a circuit, but you want it to be the largest potential difference, you must not have current flowing, okay. You must not have current flowing because when current is flowing, you cannot get the maximum potential difference because internal resistance is activated, okay. So that is the difference between them, the main difference between them, okay. So the units, okay, lastly is the units for potential difference and also EMF. They are both the same, okay. So the units for potential difference and EMF is volt, okay, is volt. So this one is V or LT, or this one is equal to joule per coulomb. Remember the formula just now? The V is equal to work done per unit charge. The unit of this one is joule, work done. This one is charge coulomb, so joule per coulomb, so it's volt equivalent. So these two units are actually equivalent. You can use either volt or joule per coulomb. But normally when we use when we talk about potential difference or EMF, we always refer to volt, and because of that, we sometimes call, okay, potential difference, which is actually equal to voltage, okay, is equal to voltage. But EMF, the question is it you can use the word voltage or not? Well, I don't encourage students to use the voltage to replace EMF, okay, unless you know what you're talking about, okay. So voltage normally refer to potential difference, and EMF is the what we call that, the ability of the battery to supply the total amount of energy per unit coulomb. So that one is different from potential difference. All right. So that's it. That is the second subtopic, which is referring to electric potential. Okay, electric potential.